This video is meant to describe the probability distribution of a discrete random variable as exemplified by the binomial distribution. So, what I'm going to focus on is the idea that, as we saw before, we can have either discrete or continuous random variables. And when it comes to discrete random variables, they can be described by a probability distribution, whereas continuous random variables are described by a probability density function. And this video is going to focus on discrete random variables and the probability distribution. The next video is going to talk about probability density functions. To illustrate the idea of a probability distribution of a discrete random variable, I'm going to be referring to the binomial distribution. So, what do we think about when we think about a binomial distribution? Let's go over an example. We're going to do, again, one of those very simple experiments where you got a bag, and inside that bag we got a bunch of marbles. And 3 of those marbles are red, and the 4th one is white. So what we're going to do is we're going to draw a marble out. We're going to record the color of the marble. We're going to replace the marble, and you're going to repeat for n equals 5 times. And the random variable is going to be the count of red marbles. So, if we go back and think about this concept of a random variable, and we thought about it in a couple of ways. One is as a mapping. So let's say we did our 5 draws and got red, white, red, red, white. The outcome of that experiment, if our random variable is the count of the number of red marbles, takes this outcome and maps it onto a number, which is going to be 3, because there's 3 red marbles. But the other way we thought about a random variable is as the set of all possible outcomes. So what is the set of all possible outcomes? Well, if I have 5 trials, I could wind up with 0 red, 1, 2, 3, 4, or 5 as the total count of red marbles. So those are the 2 different ways that we can think about the meaning of a random variable. So now what I want to think about is this idea of P at Y. And so this is a function. This is the probability distribution. And for different values of Y. So Y is going to be the outcome of the experiment. In other words, the number of red marbles. And for each one of those values of Y, it's going to provide the probability of getting that many red marbles when the experiment is done. Okay. So, let's think about this in some other terms. So our goal is to try to gain an understanding of this notation. that the probability of y is equal to the probability that the random variable y is equal to some value of y. So, how are we meant to understand that? Well, let's think about what this little p means. We can think of this little p as being a meat grinder. It's actually a function, but a function is just acts like a meat grinder in the sense that what goes in to the meat grinder is the value of y, and what comes out of the meat grinder is p at y, which I'm going to claim is equal to the probability that the realized value of the random variable big Y is equal to a particular value of little y that we observed. Now that's pretty abstract, so let's attach some numbers to this. So if we think about a binomial experiment, we can say, okay, what happens, if we take the number 1, and so by this number 1, what I'm referring to is that when the actual experiment is done, that we get one red ball, one red marble. And what comes out of the other end is the probability, p at 1, is equal to the probability when the experiment is done that the random variable y, and remember the random variable y consists of the set of all possible outcomes. There's a random variable y, the set of all possible outcomes, that when you do the experiment, the observed value of the random variable y is actually going to be 1. In other words, there's going to be one red marble. So that's how we can think about the meaning of this expression. So for each possible outcome of y, 1 red marble, 3 red marbles, 4 red marbles, we're going to calculate the probability that the random variable actually takes on, actually has that value of 1, 2, 3, 4, etc. when the experiment is done. So what we're after is probability of y, which is equal to probability that the random variable y is going to actually have that particular value when the experiment is run. And the way we're going to calculate that is with a formula, and the formula is going to be n factorial over y factorial n minus y factorial pi to the y 1 minus pi to the n minus y. Now, I'm just giving this as where we're going to wind up. What I need to talk about first is the whole idea that the experiment that we've done, drawing marbles from a bag, is a binomial experiment. And so once I can convince y'all that we're dealing with a binomial experiment, then I'm going to go on and say, oh, this is the correct formula that we'd use to calculate p at y. So let's go back and think about what a binomial experiment is and why drawing marbles from a bag actually is a binomial experiment. So, number of features of a binomial experiment. First is the outcome is binary. There's only 2 possible outcomes for every trial. Either a red ball, a red marble, or a white marble. And somewhat arbitrarily, I'm going to consider this a success, and I'm going to consider this a failure. So we're going to do a bunch of trials, and the outcome of any one trial is going to be binary. Only one of 2 possible outcomes, one of which deemed a success, the other deemed a failure. we've got a bunch of trials. We've got n equals 5 trials, and these trials are independent. And the concept of independence is an important concept in statistics. And what it means is that the outcome of any one trial doesn't have any effect whatsoever on any of the other trials. So if I get a red ball on the first trial, that doesn't have any effect on whether the outcome of the second trial is going to be a red ball or a white ball. And that comes back to this idea that when we do our experiment, we always replace the ball, always replace the marble after we have recorded its color. Third idea is we've got a random variable, and the random variable is going to be the number of red balls, number of red marbles, which is equal to the number of successes in the 5 trials. And this may be overkill, but just to reiterate, the concept of a random variable, which is so important, we've seen it in 2 different contexts. One is as a mapping, so that would take red, red, white, white, red, and map that onto number 3. Or the other way we can think of it is all possible values, the set of all possible values, number of red marbles in 5 trials. And the fourth thing is the probability of success is constant and is represented by the symbol pi. And in this case, the value of pi is going to be equal to 0.75 because we've got 3 red and 1 white marble. So in any trial, the probability of success, the probability of getting a red marble is 0.75. So if we now come back to what we're trying to do, which is to understand probably y equals probability that, I should write this out as probability that the random variable y is going to have any particular value of y. That's what we're trying to understand, and we can think, for example, that the probability of 3, in other words, when we do our 5 trials, the probability that we get 3 red marbles is equal to the probability that our random variable, once again, is a set of all possibles. It could be a 0, it could be a 1, it could be a 2, it could be a 3, it could be a 4, it could be a 5. That's the whole concept of randomness. That when we do the actual experiment, that the realized value of the random variable y, which could be any of these things, is actually going to turn out to be 3. And so we need a formula to be able to calculate that. And the formula we're going to use to calculate that is the probability of y is going to be equal to n factorial over y factorial n minus y factorial pi raised to the value of y 1 minus pi raised to the value of n minus y, where again we can just think of what these things are. That is 0.75. That's the probability of success. 1 minus pi is 0.25. That's the probability of failure. N is equal to 5. And that's equal to the number of trials. And what's y? Y is the number of red marbles. So again, if we go back to thinking of the function as being our meat grinder, there's a little meat grinder. What goes in here is y, and all this algebra calculates what comes out the end, the probability that the random variable y, which could take on any number of values, is going to have some particular value of y. And what we're going to see, for example, is if y is equal to 3, if we're asking ourselves, what's the probability when we actually do this experiment of getting 3 red marbles, that the probability that the random variable y, which could be 0, 1, 2, 3, 4, 5, because it's random, is actually going to turn out to be 3, is going to be equal to the value of 0.264. And now I want to go over how this particular equation would yield that result. So, what I want to attempt to do with this slide is to justify that probability of y, which is equal to the probability that a random variable y is going to have some particular value of y when you actually do the experiment, is equal to this thing, which from a practical point of view, when we actually do the calculations, is going to be n factorial over y factorial n minus y factorial pi to the y 1 minus pi to the n minus y. So let's begin with a simple case. Let's think about the probability of 1. In other words, that when we actually do the experiment, the probability we're going to calculate is the probability when we do the experiment that the random variable y that could take on a 0, 1, 2, 3, 4, or 5 is actually going to be the value of 1. So how could we get 1 red marble? Well, we could get a red marble on the first draw, followed by a white marble, another white marble, another white marble, another white marble. What's the probability of that occurring? Well, the probability of getting a red marble is 0.75, and then the probability of getting 4 white marbles in succession would be 0.25 times 0.25 times 0.25 times 0.25. And that's what we've shown here. We calculate the probability of getting 1 red marble followed by 4 white marbles. But hey, there's other ways in which we could get 1 red marble. I mean, we could initially get a white marble, then a red and a bunch of whites. Or we could start off with 2 white marbles, then a red and 2 whites. So when it comes down to understanding this equation, we've got 2 bits. We've got this bit here and this bit here. So the first thing is this pi raised to the power of y, 1 minus pi raised to the power of n minus y. So this part here, this right-hand part, is going to be 0.75 times 0.25 times 0.25 times 0.25 times 0.25. So that part is pretty obvious. The second part that's not so obvious is recognizing why we've got to multiply that by the number 5. Where does that number 5 come from that says that, okay, there are 5 different ways in which we could get 1 red and 4 white. And don't worry about that. Just know the formula, and the formula is n factorial over y factorial n minus y factorial. So in this case, it would be 5 factorial, because remember, n is the number of trials. In this particular case, we're thinking about one red ball, it would be 1 factorial times 4 factorial. And that is equal to 5 divided by 1 times what's 4 factorial? 5 factorial will be 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. This cancels out, and we're left with 5. So we've got 5 different ways of getting 1 red ball and 4 white balls. So that's an explanation of this very important formula that's shown here, like that. Okay, and we could, if we wanted to, we could repeat that process for a situation in which we've got, thinking of 2 red marbles. So, 2 red marbles. We could get a red marble on the first draw, a red marble on the second draw, followed by 3 white marbles. There we go. Right there. But there's 10 different ways of getting 2 reds and 3 whites. And that's calculated as n factorial over y factorial n minus y factorial, which is equal to 5 factorial over 2 factorial, 3 factorial, and that would be equal to 10. So we could repeat that for each one of those different combinations. So we need to stop there and think about where the heck we actually are. We're going to stop there and think about where we are. Okay, we're just about ready to begin. We're going to start again on 4, 3. No, we're not quite ready. Not quite ready. I think we're about ready to begin. 4, 3, 2, 1. So, what we're really trying to understand is the idea of a probability distribution, which takes for each value of y and calculates the probability that the random variable y will have that particular value of lowercase y when the experiment is actually run. And we can express this probability distribution in different ways. We can express it as a formula, and we saw that probability of y is equal to n factorial over y factorial n minus y factorial onto pi to the y, 1 minus pi raised to the n minus y. So we can express the probability distribution as a formula. We can also express it as a table, and that's what I've done here. And it's another opportunity to reinforce this concept. So, y, a particular realized value, the number of red marbles that we observe when we actually do the experiment. And so what we're trying to do is, for each one of those possible outcomes, determine the probability that that's what we're going to observe when we actually do the experiment. So again, we can think of this capital Y as being the set of all possible outcomes. And this function P at Y calculates the probability of any one of these values of the random variable being realized once we do the experiment. And so if we come up to this formula here, and we assume we've done 5 trials, n is equal to 5, and pi, the probability of getting a red ball, is 0.75, then, for example, if we consider this right here, what does that mean? Well, that just arose by taking this value, this formula here, and plugging in 5 factorial, 3 factorial, 2 factorial, 0.75 raised to the 3, 0.25 squared, and that would equal 0.264. So 0.264 represents the probability. Come back up here. It represents the probability that our random variable y, which might be any one of these different numbers, actually turns out to be the value of 3 when we do the experiment. Another way in which we could represent the outcome or a probability distribution, so we saw it could be represented as a formula. We saw it could be represented as a table, and we can also represent it as a graph. And here we see a graphical representation which shows, for example, that the probability of y is equal to 1 is equal to 0.015. The probability when we do the experiment of observing 2 red balls is going to be 0.088. And the probability of 3, the probability of the random variable capital Y, is going to be equal to 3 when we do the experiment, is going to be equal to 0.264. So that's the whole concept of a probability distribution. And the main thing that I really want you to remember, I want you to understand this idea right here. That P at Y means the probability that our random variable is actually going to have a value of this lowercase y when we do the experiment. So that's probability distribution. The next topic is going to be probability density function.